Welcome to today's paper reading. Today's paper is titled, Meta-Rewarding Language Models, Self-Improving Alignment with LLM-as-a-Meta-Judge. This paper was published on the AR14 preprint by Tianhao and colleagues from Meta-Fair, University of California, Berkeley, and New York University. Large language models, LLMs, are increasingly surpassing human knowledge across various domains. Traditionally, enhancing these models has been resource-intensive, relying on costly human data. However, recent advancements, such as self-rewarding mechanisms, have demonstrated that LLMs can improve by evaluating their own responses, reducing dependency on human labelers. Despite these advances, existing methods primarily focus on improving model responses, leading to rapid saturation during iterative training. This saturation occurs because the model's judgment capabilities are often overlooked. To tackle this, we propose a novel meta-rewarding step in the self-improvement process. This involves the model evaluating its own judgments, and using this feedback to refine its judgment skills. This unsupervised approach has shown significant improvements in the model's ability to judge and follow instructions, as evidenced by the win rate improvements on Alpaca Eval 2 and ArenaHard benchmarks. The introduction of this paper discusses the significant advancements in large language models, LLMs, and the importance of instruction tuning in their training. However, the acquisition of human-generated data for this process is costly and time-consuming, and the quality is limited by human capabilities. The super-alignment challenge aims to control super-intelligent AIs, and self-judging by the eye is presented as a promising solution. The paper introduces the meta-rewarding method, which includes a meta-judge role to evaluate the model's own judgments, aiming to improve both the acting and judging skills of the model. Figure 1 illustrates the meta-rewarding iterative training scheme. At each step T, the language model performs three roles. As an actor, it generates responses to given instructions. As a judge, it assigns rewards to these responses. And as a meta-judge, it evaluates its own judgments. The judgments are utilized to create preference pairs that enhance the model's acting ability, while the meta-judgments are used to create preference pairs that improve its judging ability. Both sets of preference pairs are combined to train the model for the subsequent iteration, thereby enhancing both its acting and judging skills. The meta-rewarding method involves an iterative self-play process where the model starts with an initial seed model and an instruction-tuned large language model, LLM, without any further human-supervised training data. The model assumes three main roles. As an actor, it generates responses to given prompts. As a judge, it evaluates and scores its own responses. And as a meta-judge, it compares the quality of its own judgments. The training process begins with the actor generating multiple response variations for each prompt. The judge then evaluates each response using an LLM-as-a-Judge prompt and generates a score. The meta-judge compares two judgment variations to determine which one is better, using an LLM-as-a-Meta-Judge prompt. This iterative process aims to improve the model's capability both as an actor and a judge. Figure 2 illustrates the prompt utilized by the meta-judge to compare two given judgments. This process involves the meta-judge evaluating the accuracy of two judgments based on a predefined rubric. The prompt includes the original user prompt, the response generated, and the two judgments to be compared. The meta-judge then determines which judgment is more accurate according to the rubric, providing a clear and structured method for improving the quality of judgments in the iterative training scheme. Figure 3 illustrates the progression of the length-controlled, LC, win rate as meta-rewarding iterations are applied. The LC win rate shows a significant increase with each iteration, eventually approaching the performance level of Claude Opus. This improvement is attributed to the meta-rewarding process, which enhances the model's evaluation capabilities. In contrast, the self-rewarding with LC baseline does not see the same level of improvement, primarily because it lacks the judge training component that meta-rewarding includes. This highlights the importance of judge training in achieving higher win rates and better model performance. In this section, we discuss the experimental setup and evaluation methods used in the study. The experimental setup involves using the Llama 3-8B instruct model as a seed model, which undergoes supervised fine-tuning on the EFT dataset. This setup is followed by meta-rewarding iterations to further refine the model. The evaluation methods include assessing the model's ability to follow instructions as an actor and its capability to model rewards as a judge. Additionally, the model's performance is compared against a self-rewarding baseline. The instruction following evaluation shows significant improvements in win rates, particularly on the alpaca eval benchmark, with a fine-grained analysis indicating enhancements across various categories. The model also demonstrates improved performance on complex and challenging prompts, further validating the effectiveness of the meta-rewarding approach. Table 1 presents the evaluation results of the alpaca eval benchmark, highlighting the significant improvement achieved through meta-rewarding training. The initial seed model, Llama 3-8B Instruct, starts with a length-controlled, LC, win rate of 22.92% against GPT-4 Turbo. By the fourth iteration of meta-rewarding, this win rate has increased to 39.44%. The table also notes that the average response length remains stable across the training iterations, indicating the effectiveness of the length control mechanisms employed. Figure 4 presents a detailed analysis of the length-controlled LC win rate on the alpaca eval benchmark, categorizing 805 test prompts into 20 groups. The study reveals that meta-rewarding significantly enhances performance across 17 of the 18 categories compared to Llama 3-8B Instruct. Notably, the overall LC win rate experiences a substantial rise from 22.9% to 39.4%, surpassing GPT-4 and nearing the performance of the Claude Opus model. This achievement is particularly noteworthy given the model's 8B parameters and the absence of additional human data beyond the seed model during training. Table 2 illustrates the performance of meta-rewarding on the ArenaHard dataset, which consists of high-quality prompts from the chatbot Arena. Despite the distributional differences between these prompts and the open assistant-like prompts used in training, meta-rewarding demonstrates a significant improvement. Over 4 iterations, the method achieves an 8.5% increase in score compared to the seed model, validating its effectiveness in handling complex and challenging prompts. Table 3 evaluates the correlation between the judge models and GPT-4 on responses generated by the Llama 3-8B Instruct Seed model. The table shows that the Llama 3-8B Instruct Seed model has an agreement with GPT-4 of 61.03%. The meta-rewarding LLM, after 4 iterations, achieves an agreement without ties of 78.42%. Notably, the self-chosen pairs setting demonstrates higher agreement without ties, indicating the effectiveness of the meta-rewarding methodology in refining the model's judgment capabilities. Table 4 illustrates the effect of the length control parameter rho on alpaca eval, showing its significant impact on both the win rate and the length-controlled LC win rate. A larger threshold for rho decreases the model's generation length, while turning off the length control mechanism, rho equals 0, increases the win rate but negatively affects the LC win rate and lengthens responses. Opting for a balanced length control parameter ensures a balanced final performance. Additionally, comparing the length control mechanism with a naive filtering based on response length, filter greater than 2500, reveals that the latter negatively impacts both win rates, underscoring the effectiveness of the length control mechanism. Table 5 presents the statistics of the Meta-Judge, highlighting the evolution of biases. Initially, the Meta-Judge shows a preference for higher score judgments, with a 36.96% higher win rate in the first iteration. By the second iteration, this bias intensifies to 97.68%. Additionally, a positional bias emerges, with the Meta-Judge increasingly favoring judgments in the first position. This bias is evident from the 47.79% preference for same-score judgments in the first iteration, which rises to 87.75% by the second iteration. These biases significantly alter the scoring distribution, pushing it towards a full score of 5. Figure 5 illustrates the significant shift in the scoring distribution of a judge model trained using a Meta-Judge. The training process notably influences the judge to concentrate more on assigning higher scores. This shift is quantified by the increase in the mean score from 4.1 to over 4.7 after undergoing 2 iterations of training. This change underscores the model's enhanced tendency to rate responses more favorably, which could be crucial for distinguishing between varying quality levels of responses. In the realm of aligning large language models, LLMs, with human values, significant efforts have been directed towards 2 main strategies: aligning with a reward model or directly based on a preference dataset. For instance, Ziegler et al., 2019, and others have trained a fixed reward model from human preference data and used it to train via reinforcement learning, such as proximal policy optimization, PPO. To reduce engineering costs, Wu et al., 2023, introduced the contrastive policy gradient, which outperforms PPO without needing a value function. On the other hand, direct preference optimization, DPO, by Rafaelov et al., 2024, avoids reward model training and directly trains the LLM using human preferences. Additionally, using LLM-as-a-Judge for evaluation and training reward models has become standard practice. For example, Li et al., 2024, and others have investigated how to construct datasets for training a LLM-as-a-Judge, emphasizing self-improvement of judgment skills. The concept of super-alignment involves aligning a model that surpasses human level. This includes using models to assist human supervision, automatic search for problematic behaviors, and AI producing feedback for training AI, such as constitutional AI by Bai et al., 2022b. In this study, the authors propose a novel meta-rewarding mechanism to enhance the judging capabilities of models. This approach introduces a meta-judge that assigns rewards to selected judgments, addressing a key limitation of the self-rewarding framework by ensuring the judge is trained. To support this method, a new length control technique is introduced to prevent length explosion during training with AI feedback. The effectiveness of this method is validated through benchmarks such as AlpacaEval, ArenaHard, and MTBench, showing significant improvements over models like Llama 3-8b Instruct and surpassing the self-rewarding and SBPO baselines. Notably, the model's judging ability shows strong correlation with both human judges and advanced AI judges like GPT-4-1106 Preview. These findings strongly suggest that self-improvement without human feedback is a viable path towards achieving super alignment. Thank you for watching.